If you recall, yesterday we talked about building double integrals in polar coordinates. So we had a quick review of polar coordinates. Here's an even quicker review of polar coordinates. When we're describing a point in R2, we really just need two numbers. We just need two numbers. This is why your address has two numbers attached to it. We're describing a point in two-dimensional space, so we need two numbers attached. If you have an apartment, that's just like a third. That's that one you work out when you get there. The location on the ground is two numbers because it's a location on R2. Not all of R2, just some local area. We don't have a city that spans like, you know, an infinite space yet. So since we're just describing a point in R2, there should be a way to convert from one set of coordinates to the other. And there is. So if we have r and theta, x is r cosine theta, y is r sine theta. And if we have x and y, then r is just going to be the square root of x squared plus y squared. And the tangent of theta will be y over x. Instead of saying tangent inverse like I did yesterday modulo flex day on Tuesday, we should say the tangent of theta will be y over x, and then we can worry about what coordinate, what quadrant we are in. The problem that arose with regards to what we're doing, that is building double integrals, is that one of the factors in our integral is this dA factor. It represents a small piece of area over which we're assuming the function is constant. With rectangular coordinates, dA was just dx times dy. dx is a small change in length, dy is a small change in length, so their product will be a small chunk of area. The problem in polar coordinates is that theta does not represent a length. Theta represents an angle. So d theta is a small change in angle. And so dr d theta does not represent an area. So we had to use the arc length formula and multiply by r, how far that little piece of d theta is from the origin. That will make that piece of d theta longer. So once again, if we think about a piece of d theta, d theta as a length will change depending on how far we are from the origin. So here's a little angle, d theta. If we're really close to the origin, then d theta is shorter than if we're really far from the origin. So d theta tells us a length based on how far we are from the origin. So as r increases, d theta represents a larger change in length. So that's where the r comes from. And then our usual calculus thing. This is all curvy. And when someone says, hey, this is all curvy, so this r d theta is not going to be a little bit of a little rectangle, the response is in a very Newton, don't take your pen off the paper style. Well, if we make d theta small enough, then it's not that curvy. If we look close enough, it's pretty flat. Relying on the same concept of the flat earther. It's like, oh, well, look around. See, the ground is flat. We're clearly not on a round thing. Never mind the fact that we're just looking really close. You know what I mean? So we want to get into different coordinate systems. Here are two different coordinate systems that we use for R2: rectangular coordinates and polar coordinates. We're starting to incorporate angles in how we measure where things are. So now we want to jump up to R3, and we're going to have 3 different kinds of coordinates. So we want to talk about cylindrical coordinates and spherical coordinates. So now we want to jump up to 3-dimensional space. Once we get the hang of describing things in these different coordinates in 3-dimensional space, going further into 4-dimensional space, that will be less of a problem. I mean, we'll have to deal with the fact that we're thinking about things in 4-dimensional space. We'll have to figure out how we're going to describe those things, to those ideas to other people, but conceptually, it's pretty well organized. Now, rectangular coordinates, this is all 3, these 3 systems are for R3, for 3-dimensional space. Rectangular coordinates are the ones that you're familiar with, X, Y, and Z. Let's talk about cylindrical coordinates. Cylindrical coordinates are just polar coordinates plus height. So cylindrical coordinates are just polar coordinates plus height. So where rectangular coordinates use a floor of X and Y and then put Z on top of it, cylindrical coordinates just use a floor of R and theta and put Z on top of that. So every semester I attempt to draw this, and it's always a bad idea, and yet it's kind of like a Rocky and Bullwinkle situation. This time, for sure. So I'm going to grab the same point that I had in the picture above. There's a point with an X and a Y coordinates. And this point can also be described with R and theta. R is still the distance from the origin to this point on the floor, and theta is still measured from the positive x-axis towards the positive y-axis being positive. That's the first quadrant being positive. And then just on top of this point in the plane, either xy or r theta, we just have a height above that. So this point in space will be either x, y, z, or r, theta, and z. So these are cylindrical coordinates. Cylindrical coordinates are just z on top of polar coordinates in the same way that rectangular coordinates are just z on top of x, y coordinates, Cartesian coordinates. If we think about the issues that we have with creating a double integral in the context of a triple integral, remember what we need for a triple integral. We have a triple integral over some solid w of some function. We'll need this dv. We need a factor of dV, and that has to be a volume. And so this dV dV can be, we have to have 3 lengths to build the dV. So in rectangular coordinates, no problem. dx, dy, dz. dx is length, dy is length, dz is length. dx, dy is just the area in the xy plane. dz is just some small change in the height. And then we assume that the value of the function is constant through that little cube. In polar coordinates, we have the same problem. d theta is still not a length, it's a change in angle. But because we're just taking polar coordinates and tacking z on top, we just have to tack the r on to turn d theta into a length. r d theta is a length. And then we have a dr. And the dz in this dv is the same as the dz in the rectangular dv. We still need that r to turn d theta into a length. How we build the integral works the same as it did in all the other times we were building a double or a triple integral. What is r between? What is theta between? What is z between? Now let's talk about spherical coordinates and then see what we'll have to do to get length out of our spherical coordinates. First, let's set up our spherical coordinates. And actually, before we start building triple integrals with spherical coordinates, let's take a look at the concept of rectangular to cylindrical to spherical coordinates. It's just increasing the number of values we replace with an angle for the measurement. So for spherical coordinates, I'm not going to draw it on top of here. It'll get messy, like messier than it already is. With spherical coordinates, we're not going to use the XY plane at all. We're not going to tie ourselves to that. In spherical coordinates, we're only going to use one of the coordinates as a length. Because we have a point, if we have a point in 3-dimensional space, it is some distance from the origin. So let's draw a set of x, y, z coordinates because it's familiar. And let's put a point out here. There's an XY. I am going to borrow theta from our polar coordinates. So theta is going to be the angle from the origin, from the positive x-axis towards the point. So this point is still xy, 0 for height, or r theta and 0 for height. So we're going to put a point above In spherical coordinates, or sorry, in rectangular coordinates, this is the point x, y, z. So I'll put this point up here at z. This happens at x. This is where we'll find y. R is the distance from the origin to this point. The coordinates of this point in 3 dimensions are x, y, and z. Or r, theta, and z. Or we can describe it with spherical coordinates. In spherical coordinates, we're just going to use one distance, and we're going to call it rho. I'm not really a fan of using rho because I think it just comes from teaching trig and using theta, Greek letters for angles and other letters for lengths. And now I'm going to be using a Greek letter for a length. But we don't have, even though we have tons of options, we don't have lots of options. So we're going to use a lowercase rho. That's going to be our length. That's the distance from this point in 3 dimensions to the origin. So rho is this distance. So rho is going to be the distance from the origin to the point. Theta is going to be the same theta as in polar coordinates. That's why we get to use theta again. So it's the angle that we rotate, that we measure from the positive x-axis to a terminal side of a point directly underneath our point in R3 or above. And then we have another angle, phi, which is measured from the positive z-axis down to the point. So the theta is the same theta as in polar and cylindrical coordinates. And this new angle phi is measured from the positive z-axis to the point. So that will be our third coordinate. We're in 3-dimensional space, so we're going to need 3 coordinates to describe where we are. We can either use 3 lengths, 2 lengths and 1 angle, or 1 length and 2 angles. Can't use 3 angles because then we have no concept of distance. Any questions? It's pretty cool. It's just a different way of describing someplace in three-dimensional space. The reason we want to stop and look at this picture for a while is because we're waiting for that moment when you're like, well, hang on a second, why didn't we measure it this way? And the answer is going to be, stuff doesn't work as good when you measure it that way. Yes, so one is like polar coordinates with extra length. That's exactly what cylindrical coordinates are. Cylindrical coordinates are just polar coordinates, and then we tack z on top of that. And then someone comes along and says, well, hang on a second, what if we just want to use one length, the distance from the origin to the point? Where are we going to, we just had to decide, like I was there, we just had to decide where we were going to put the two angles, because we knew there were going to have to be two. And so someone suggested, hey, why don't we use the theta that we used in polar coordinates? And then we just had to decide where we were going to put our angle phi. So it's going to be, we decided it was going to be measured from the positive z-axis. That's the one that made the most sense in the calculations. Any questions? That was the other section. That was the other suggestion. What if, like I was there, what if we measure the angle down to the XY plane? And that's less convenient because that's still tied to, even though we get the length, I think the reason that we didn't go with that is that that's still tied to the X and Y. And this way phi is more directly tied to the z-axis. Once we see where the rho, phi, rho, theta, and phi are, then we just have to get used to not necessarily converting from one to the other, but we have to get used to thinking in these different coordinate systems. So we didn't talk about how to convert from rectangular to cylindrical, or from cylindrical to rectangular, because all we did was take our XY plane or our R theta plane and tack a height on top of it. So z equals z, put that at the end of our polar coordinate stuff, and we're all set. However, now we have new things. Now we've got new stuff running around. So what is, if we have a point rho, theta, and phi, how do we write down what x is? How do we write down y? How do we write down z? This is a significant question. So that's the first thing. What are x, y, and z in terms of rho, theta, and phi? Also, what are rho, theta, and phi in terms of x, y, and z? But our primary concern is going to be, what are x, y, and z in terms of rho, theta, and phi? So if you've been in my class before, you know that by me writing this, you can tell that I'm not going to tell you, because I wrote it right where I would write it. If I was going to tell you what x, y, and z are in terms of rho, theta, and phi, then I would have just written it down. But instead, I might call, oh, we got to write x, y, and z in terms of rho, theta, and phi. And then students that have been in my class before, I was like, dude, we know this maneuver. When you do this, when you say we have to find this, you don't mean we, you mean us, don't you? I'm like, no, what are you talking about? I'm sure I'll get to it by the end of the week. Then you remember I'm a DM, and therefore I love cliffhangers. My current Saturday night game, I've ended the last 2 sessions on essentially you're staring into a long, dark hallway. We'll pick up next time. It's just cliffhanger after cliffhanger. One of these days we're gonna end a session, and it'll just be like back at the tavern having some drinks, and nothing will happen, and they'll think it's really weird, and they'll be really suspicious because of the sequence of cliffhangers that I put in front of them. And they'll be stressed about that, and the non-cliffhanger will be a cliffhanger. So that's all beside the point. So I'm not going to tell you what rho, phi, what x, y, and z are in terms of rho, theta, and phi are, because it's a trigonometry problem, and it's useful, and it will help you think about what's going on in these coordinates. If I just tell you, you won't have to think about these coordinates. You'll just try to rely on some equations for conversions. But if I make you do it, I just have to define what rho, theta, and phi are, and then I get to force you to do the work. This is lazy teacher strategy 101. Here's the other thing that we have to worry about. Here, we're just learning how to describe things in these spherical coordinates. We're also going to have to figure out what's going on in a triple integral, where we have a function of rho, theta, and phi, and we have this dv factor. dv is going to have to be a volume because of the way we're thinking about it. But I need 3 lengths. D rho, no problem. That's a length. No problem. D rho is a length. D theta, not length. We need some extra factor to turn d theta into a length. Now, if you're thinking, why don't we just use r from before? We don't have an r. There is no r in these spherical coordinates. That's something from cylindrical coordinates. We borrowed theta from the cylindrical coordinates already. We can't be borrowing theta and r from our cylindrical coordinates. That'd be like, well, hey, neighbor, I see you have 3 cars. Can I borrow one of them? And they'll probably be like, all right, no problem. Hey, neighbor, I see you have 3 cars. Can I borrow 2 of them? They're going to be super suspicious. They're going to be like, oh, dude, are you just stealing my cars and selling them to Carvana? And you're like, oh, no, yes. Then the other d variable we have is d phi. And that's also not length. So we're going to need 2 extra factors in here to turn dv into a volume. D rho is already a length, but we need a factor for d theta to get a length. And we'll also need another factor to get d phi into a length. They're both going to be about how far we are from the origin. Now, for the turn d theta into a length, d theta is dependent upon this length down here, how far we are from the origin in the xy plane down here on the floor. We can't use r because there is no r, but we can figure out what r is in terms of rho and phi, or rho, theta, and phi. So here are the questions that I need to answer so that spherical coordinates will magically snap into place. And if I just write these things down for you, everything will become perfectly crystal clear and we won't even have to do any problems at all. You'll be like, oh, dude, we totally get it. Thanks for writing that down for us. All I had to do was copy it down one time and I will know this forever. So I just have to write down what X, Y, and Z are in terms of rho, theta, and phi, and then tell you how to write dV with a d rho, d theta, and d phi so that it'll all make sense and everything will become perfectly crystal clear and you'll never struggle in math ever again. So here's the secret to the mathematical universe. Ah, rats, look at the time. I guess we're going to have to stop for today. Everything was going to be so easy. I was just about to like matrix style program you with all of math. I'm just kidding. I'm stopping now because I want you to think about it. Because it's important that you start practicing thinking in terms of spherical coordinates, even though we just started talking about it today, even though I've done 0 problems. It's kind of like the teaching a computer to play chess. I don't think they just told the computer what the different. I think if you want to count, if you want to count as teaching a computer to play chess, you pretty much got to tell the computer what the moves are. Here's what the pieces do. Here are your conditions for victory. And, teach it the rules, and then let it go. Let it make mistakes and learn from them. You know what I mean? Same kind of thing. I don't want to teach you the strategies. I want to give you the opportunity. I'll phrase it that way. I'm giving you the opportunity to think in spherical coordinates because it's new and weird and interesting. And I don't want to take the fun out of it, of figuring out how to describe X, Y, and Z in terms of rho, theta, and phi. I don't want to take the fun out of figuring out how to write dV so that it's a volume. How do we turn d theta into a length? How do I turn d phi into a length? So that's your task for this weekend. And I'll see why chapter 17 hasn't come up yet. It's because I don't want you to be distracted from the actual thing that you want to be thinking about, that you want to be thinking about. Want to. All right, that's going to do it for today. That's going to do it for this week. Everybody have a good weekend. I'll see y'all on Monday. Everybody have a good weekend. Thanks for playing.